Let's read it. There's two.
Yeah, but that changes how we're applying the stability.
So, are we ready? Let's get started. So, did everyone get the email about and was able to connect to the new website? Try. Well, everything will be posted there, except I can't stream the videos from that site, so we'll be loading them onto YouTube for now. Okay? Our YouTube channel, if you didn't know, there's Secret YouTube. Anyway, there are a couple of small typos in offset 5, 1 minus sign, and probably 1B, and another minus typo, but that's corrected. Okay. With the impending move and all the confusion about it, I want to put off when we'll take up the lecture. We'll find a time to do that. But we'll wait till we get resettled in our digs. All right. Okay. So we're talking about controlling quantum coherence in atoms with optical fields, with lasers. And as we have said, generally speaking, that you can't really do that if you tune to resonance with an optically allowed transition, because that is a very short lifetime. So the way in which we can deal with that ultimately will always involve not going to resonance, to be sufficiently far off resonance. And in that circumstance, as we'll see, we will be able to control quantum coherence. The most straightforward thing to think about, first of all, in the context of a two-level atom, what we saw is that when the detuning is sufficiently big compared to the Rabi frequency, we can adiabatically eliminate the dynamics of the excited state. And in that sense, we say the excited state probability amplitude is slaved to the dynamics of what goes on in the ground state. And we can then just relate the excited state to the ground state in this way. And when we plug that back into the equation of motion for the ground state probability amplitude, we get something that looks like this, where we have a Hermitian-like phase evolution, and then we have a decay term, okay? And this phase is related to an energy level shift we call the light shift, also known as the AC Stark shift, that is induced on this level due to this off-resonant laser field, okay? And that light shift is equal to, in this limit, where delta is big compared to the Rabi frequency, it's equal to the saturation parameter times delta, basically, factors, okay? And in particular, if the detuning is big compared to the line width, the natural line width of the system, as I say, 1 over the lifetime of the excited state, then this is approximately equal to this, which scales like the intensity of the laser over the detuning, okay? Because the Rabi frequency goes like the electric field. The decay of the ground state is characterized by what we call the photon scattering rate. And the scattering process here is scattering a photon off of the atom. There's my atom, laser comes in, and a photon is scattered from the laser beam into 4 pi. And there's a rate at which that happens, that is the photon scattering rate, which is the absorption cross-section times the rate at which photons are coming in, right? And that is the process by which I absorb and emit, okay? This photon is scattered in this regime of low intensity, that's to say where the neutrino is big, is elastic scattering. This photon has the same frequency as the input, right? That's always a little bit confusing. You think, oh, I get from here to there. I spontaneously emit, therefore my photon has to have that frequency. No. It's in steady state, the dipole, this is like a Lorentz oscillator. And this is just oscillating at the frequency of the drive. Therefore, it radiates radiation at the frequency of which is being driven, which is the laser frequency. That's what we call elastic scattering. Okay. We'll come back to that. I hope talk about more about the problem of what's called resonance fluorescence. Well, this is near resonance fluorescence. It's a very important problem in the whole theoretical development of our understanding of classical versus non-classical light. Anyway, I digress. Yes, sir.
Will the emitted photon differ from the incoming photon by the star shifter?
You mean in terms of the frequency? No, it will be elastic. It will be a delta. It will be exactly at that frequency. To the degree to which this is low intensity. So it's purely elastic. What it will differ by is the recoil. So the photon has momentum. And because it has momentum, the atom absorbs some momentum and emits some momentum. And the difference in that momentum goes into the kinetic energy of the atom. And there's a recoil shift. Yeah?
I guess I'm a little confused. So how does that work out that
The recoil? That's not in here. Because to do that properly, I have to quantize the motion of the atom. And we're keeping the atom fixed. So to the degree to which we are not including the motion of the atom in our description, you won't see it. To do that properly, we'd have to add, a p squared over 2m into the Hamiltonian for the motion of the atom. But that's a whole other story. Yeah?
The fluorescence is omnidirectional, is it?
Yeah, I don't want to go too digress. I digressed, I'm sorry, I piqued everyone's curiosity, but it's a long story and we'll get there. Let's put it aside for now. I don't want to fall farther behind. We're already doing it. Okay? I appreciate everyone's curiosity because I don't want to belch that. We will get there. Right. So this scattering rate, we can think about one way to say what is the rate, it's the probability to be in the excited state times the rate of spontaneous emission. And the probability to be in the excited state is that in the steady state. And importantly, this scales differently from the light shift. The scattering rate scales for detunings that are off resonance, scales like the intensity over the detuning squared, whereas the light shift scales like the intensity over the detuning. And what that means is that gives us a possibility to create coherent quantum phases on this level with little dissipation. Because if we detune sufficiently far from resonance, this will be negligible compared to that. And we'll just pick up whatever phase shift we want on this level. And we do that all the time. We meaning the people actually in the lab. It's the way. Right. Now, again, I want to emphasize another factor. I mean, this difference here is really related to the fact that this is a kind of dispersive effect, whereas this is sort of a absorption effect. And you remember, if we think about the response of a dipole oscillator to a drive, there is the Lorentzian line shape, which falls off differently than the dispersive part of the line shape, right? The Lorentzian falls off like 1 over the square, whereas the dispersion falls off like 1 over the first power of the detuning. And it's for that reason that this is. So one way to understand the AC Stark shift is the way we think about the Stark shift when we think about perturbation theory and the Stark shift. That is, I put the atom in an electric field. My interaction Hamiltonian is fundamentally here E dot E. Right? That's the interaction of the atom with the laser light. And I want to ask myself, how does the energy eigenvalue of this energy level get shifted in perturbation theory, according to perturbation theory, according to this? How would you generally calculate in perturbation theory the shift of an energy level? Yeah.
You use like your unperturbed wave function.
Right.
Just energy.
So to first order, my shift in the ground state would be equal to this, right? As Matt already said. And what's that?
0.
0. Because the atom has no dipole moment if it's in the ground state. That state has parity symmetry, and the electron is probability is equally in all directions away from the nucleus, right? So we have to go to second order perturbation theory. And in second order perturbation theory, so this is the first order, I have to do the whole business of, you know, all the off-diagonal elements, right? So I would look at the energy, which is in fact equal to this. Okay, so that's exactly what that. But now, physically, what we can understand, that's a piece of mathematics, but physically what's going on? What's going on is I have an induced dipole moment. The atom is polarizable. That is to say, I stretch the electron away from the nucleus and I induce a dipole. That induced dipole is to lowest order proportional to the electric field. So my induced dipole moment is the polarizability, the real part of the polarizability, right? And then I have an interaction of the induced dipole moment with the electric field. And what's the energy of an induced dipole? If I were to ask, what's the potential energy of an induced dipole with the field, what does that equal to? Griffith's chapter something or other. And you kind of remember that there's this factor of a half. When you have the induced dipole, right? And then, of course, this is all oscillating in time, and the effective rotating wave approximation is the time average of this. So this is equal to minus 1/4 the real part of the polarizability times E squared. And I challenge you to write what we described as the polarizability of the atom, the linear polarizability that we saw using the optical Bloch equations, and you get this. They're one and the same. So physically, that's what's going on. That's why there is a light shift, because the atom is polarizable. And that induced dipole. Now, the question is that induced dipole in the same oscillating with the field or away from the field? That depends on the detuning, right? You remember my slinky? Here it is. Here's that slinky. I have a line. Here's my slinky. And now if I am tuned below resonance, then this goes in the same direction as the drive, which means alpha is positive. And since alpha is positive, this shift is negative. Whereas if I'm driving faster, then it's 180 degrees out of phase, in which case alpha is negative, in which case this is positive. So for blue detuning, I get a positive energy shift on the ground state, and for red detuning, I get a negative. We still have physics, okay? Even though there's some crazy things with matrix elements, whatever the hell that means, there's still physics. All right. So, speaking of crazy things with matrix elements, we also looked at this idea of the Dress state as the full, not just in perturbation theory, but in the context of the two-level atom, we can exactly re-diagonalize the Hamiltonian in the presence of the perturbation. That's just because we've made this approximation of the two-level atom in the rotating wave approximation. Then we don't have to do no stinking perturbation theory. We just diagonalize the whole 2x2 matrix again in our head, because we can do it. And we did it. And we have new eigenvalues and new eigenvectors. The new eigenvectors are known as the Dress states. And they are superpositions of the ground and excited state with a certain amplitude that depends on what we call the mixing angle, although we should call it the superposing angle. This has nothing to do with mixed states. It's just that, you know, in the past, people always thought the only thing that's important are the energy eigenstates, and anything else was called a mixed state. But that's a stupid term that's still out there. When you don't have an energy eigenstate, it was called a mixed state. But it's not mixed, it's pure. So, right. So we have this picture that that's helpful to think about in terms of what are the instantaneous energy eigenvalues in the rotating frame of the ground and excited state as a function of detuning. The dashed lines are in the opposite, in the absence of the laser in the rotating frame. And the solid lines, if I was a good professor, I would have got a piece of blue chalk, sorry. And they are these are these eigenvalues. And what we see here is, you know, below resonance, the ground state is shifted to negative energies, as we said, because the polarizability is positive, and to the blue of resonance, the ground state is shifted above resonance. If I go beyond perturbation theory, there's a strong superposition, and in fact, right on resonance, this is a 50-50 superposition of ground and excited state. This is the problem you solved in homework. Are you solving it now? Of adiabatic passage. So interestingly, this would be an amazing thing to do. Suppose you have your two-level atom and you're detuned very far to the red, and you very, very, very slowly sweep all the way through resonance to the blue side. What will happen if I started in the ground state? I'll end up in the excited state. This is what's called adiabatic rapid passage. Now it's kind of a oxymoron having to be adiabatic and rapid at the same time, but you have to be, according to the adiabatic theorem of quantum mechanics, which some of you may have studied, if you start in an eigenstate of the Hamiltonian and you change the Hamiltonian as a function of time, then at any time, if you change this slowly enough, and slowly enough has to be thought about carefully, you will all stay in that eigenstate of that Hamiltonian, which is a different Hamiltonian at different times. For example, if I'm changing the detuning as a function of time. And so in that case, I would adiabatically end up in that state and end up in the ground state. I have to do that slowly enough, and what slowly enough is according to the adiabatic theorem. Has to do something about this energy gap, which means really about doing things at something at a rate that's slow compared to the Rabi frequency, because this gap is the Rabi frequency, right? Right on resonance, the gap is the Rabi frequency. But you have to be fast compared to spontaneous emission, right? So you better have your omega be big compared to, you want a situation where omega is much, much bigger than gamma, so that you can be rapid, get adiabatic, and that's called adiabatic rapid passage. A very powerful technique in coherent control. Right, okay, so let us continue. One of the ways that we use this kind of off-resonant excitation is to manipulate quantum coherence between two levels that are not directly connected by an electric dipole transition. For example, I might have two magnetic sublevels in the electronic ground state that are separated by, say, a microwave. They might be hyperfine split in an atom, and I want to drive quantum coherence between them. So I have a level 1 and a level 2. I have an auxiliary excited state, level 3, by which I'm going to have a 2-photon resonance. Okay? This is what we call the Lambda configuration. And this is, as we discussed, this is Raman resonance. So Raman scattering is typically you absorb and you emit at a different frequency than Stokes. Right? And now I'm going to have a stimulated kind of effect. And we have two laser beams, laser 1 at frequency omega sub L sub 1 and another frequency at omega sub L sub 2, where this is detuned from resonance by this, and I've chosen this in such a way that maybe there's a slight difference. I'll call that little delta. Okay? So delta here is the difference between laser frequency 1 and the energy, the Bohr frequency between level 3 and level 1. Okay, so that's E3 minus E1 in units of H bar. That's the detuning of this laser from resonance. And then I have what I call Raman resonance. Well, there's going to be a little bit of. So when if the two frequency, the difference between the two, so omega laser 1 minus omega laser 2, if that is equal to the energy difference between E2 and E1, then I'm on Raman resonance, or 2-photon resonance. Okay? And so the difference between that and that is what I'm calling little delta. All right, so what you have in your homework is to write down the equations for the effective Hamiltonian of this 3-level system by effectively going to the rotating frame. doing the unitary transformation that will get rid of the explicit time dependence of these two laser drives, and then making the rotating wave approximation. So in the rotating frame and in the rotating wave approximation, I have an effective Hamiltonian. That effective Hamiltonian is the following. The excited state has an energy in the rotating frame that is related to the detuning, right? And then it has some lifetime. We'll assume that this thing spontaneously decays with some rate gamma. And so there's an imaginary part, as we discussed in the effective Hamiltonian, like that, right? We're going to take level 1 to be at energy 0, and therefore in the rotating frame we have the energy of level 2, which is the detuning, that Raman detuning. And then I have the off-diagonal elements where I have the dipole interaction that drives Rabi oscillations on this transition and on that transition. So the interaction Hamiltonian there, there'll be a Rabi frequency for laser 1, which drives me between level 1 and level 3. And then I'll have a Rabi frequency associated with laser 2. That's the electric field amplitude of laser 2. And it drives me between level 2 and level 3. So that's my effective Hamiltonian. Okay. And then, based on those equations, I can write the equations of motion. So particularly, I have the Schrödinger equation. It says that the effective state in this non-Hermitian Hamiltonian evolves according to a Schrödinger-like equation with a non-Hermitian H effective. My H effective has some amount in level 1, some amount in level 2, and some amount in level 3. So now I can write down differential equations for each of the probability amplitudes based on that equation, as we've done before. So in particular, if I look at what we want to do, we're going to assume there's a Rabi frequency associated with this laser and a Rabi frequency associated with that laser. And again, we're going to assume that the detuning is much, much bigger than either of these guys. Okay, so we're going to adiabatically eliminate in the same way that we did for the 2-level atom. We can adiabatically eliminate this amplitude in favor of these and get an effective 2-level system driven by a 2-photon transition. Yes, sir?
So why don't we do like the jump operator for?
We do, ultimately, to get correctly what will happen in refeeding of the levels of 2 and 1. Okay, but level 3 has the level 2. There is no refeeding. So for level 3, the jump operators play no role because they only affect the refeeding of the ground state. So this is actually exact for this. Now, as far as what happens with level 1 and level 2, as you will have in your homework, you will have to put in all those jump operators. But if we're interested in some of the dynamics that happen on a time scale that is short compared to the time of photon scattering, we can ignore that effect. And that's what we're going to do today. With your homework, you're going to do something Okay. So, but for level 3, we don't have to worry about that because there is no refeeding term for level 3. And level 3, according to this Hamiltonian, I'm going to get this effective Hamiltonian for that amplitude. So adiabatically eliminating this, as we saw last time, was equivalent to the steady state solution to this. So we set this equal to 0 in adiabatic elimination. And what we then get is level, the excited state is now slaved to these guys. So that's our adiabatic elimination of the excited state. And so now one writes down the effective solution without the feeding terms for the two sublevels 1 and 2 and plugs that back in. I'm not going to do all the algebra on the board. It's tedious and boring, and I'll make a mistake anyway. So I'm just going to take the chicken out of the oven and show you the finished product. And here it is. Yeah, that's right. So plugging this back in, I get the following equation. C1 dot So let me write it down and I'll explain what all these terms are and what they mean. Okay. So these are the effective equations of motion, including the decay parts of this, where each one of these guys for a certain level, either I'll call it J being 1 or 2, is equal to the light shift on that level. So this is the light shift on level 1 and level 2 due to the fact that it is being driven on an electric dipole transition off resonance. And that shifts, there's a shift on level 1 and there's a shift on level 2. It depends on the saturation parameter, which is depends on the particular intensity of that, whether it's omega 1 or omega 2, right? For laser 1 and laser 2. In addition, we have photon scattering, where I absorb and re-emit a photon driven by laser 1 or laser 2. So that's photon scattering. So each of these terms is what we had seen and reviewed in the beginning of this lecture for the two-level system off resonance, right? Just the same thing we just discussed. But now I have this other effect, and this other effect couples level 1 to level 2 and level 2 to level 1. Okay? And so I have now this additional term, something I'm calling the Raman-Rabi frequency, or R equal to RR, Raman-Rabi, frequency, which is the 2-photon Rabi frequency. And it is equal to omega 1 times omega 2 over, oh gosh, is it 2 or 4? I looked it up. Yeah, that's right. So, and this other decay term, which is
Are we worried about light shifts from like the other beam? Right, so we have 2 lasers, and it looks like our delta E sub j is only concerned with like.
yeah, we're assuming that this splitting is sufficiently big that I can ignore the light shift induced on 1, right? Alternative, it might be that this is a different polarization, and it might be that there's just no level up there. So we're treating this in such a way that 1 is only coupled to 3 and through this laser beam and not this. And 2 is only coupled to 3 through this laser beam and not that. That can be set up in some approximation, and that's what we're considering. So, just for example, this might be a splitting of 10 gigahertz, and this might be a few megahertz. And so I can basically ignore the effect. This would be so far off resonance, and as you know, the light shift falls off like 1 over the tuning. It's completely negligible. All right, so what do all these things mean? Well, this we understood. These are the light shift and the single photon scattering rates. This is, as I said, as we will see in a moment, is effectively the Rabi frequency in an effective 2-level system once we have adiabatically eliminated the 3rd state. It's like a new 2-level system, as we will see. There's this additional decay term. It's kind of a 2-photon decay effect, right? It depends on both electric fields. Now, if we're in the limit, as we want to be, to do this coherent control, where the detuning is huge compared to the line width. Okay, so let's look at in that limit. Then, well, what do we see? In that case, I can ignore this. I can ignore that. And I get that. This thing falls off like the product of the electric fields over the detuning. Whereas this thing falls like the product of the electric fields over the detuning squared. And when that is, if this, and similarly, as we discussed before, this goes like the intensity of each laser beam over the detuning. And this thing goes like, I'm sorry, the square, and this goes like the intensity over the detuning. So in that limit that I detune far compared to the line width, or the spontaneous emission rate, then over the time scale that I'm interested, if I can make this big compared to that, which I can do, right? Notice that this thing, that these guys are just related by this ratio. So if this is tiny, then this is much, much smaller than that. And over that time scale, I can ignore that. And similarly, the light shifts can be, I can make that over the time scale of interest, I can ignore this decay. Of course, it's got to be there if I want to get all the decays right, but for the time scale where this is negligible, I'm going to neglect it. So, what is this, what are these equations? Well, these equations are nothing more than the equations of a two-level atom driven between one another with an effective off-diagonal coupling. So in that limit, when the detuning is big compared to this, I have now a new Hamiltonian, a Raman Hamiltonian, we call it, which is the following. It has some energy eigenvalue for level 1. It has some energy level 2 with some energy delta E2. And then it has off-diagonal coupling between level 1 and level 2. This Hamiltonian leads to this Schrödinger equation, right? Has the off-diagonal elements here and the diagonal elements which give the phases here. But look what that's just our two-level Hamiltonian. If I can write this now, I'll call this effectively spin up, and this pseudo spin down. Then I have my two-level system as a pseudo spin in a pseudo-magnetic field, as we always have for any two-level system. So this is equal to, I have the identity part that I can care less about, and then I'm going to have, oh, I made a boo-boo. And that boo-boo was I forgot about this Raman detuning. So I got to stick that in here somewhere. That's the, when I'm not on two-photon resonance, there was this term, and I left that out. Right? Okay, so now what I have is the following. All right, let us examine this and understand what's going on. This is just an overall, this is the identity. It affects nothing about the dynamics. It just determines what we're calling the zero energy. So I'm going to just forget about, we don't want to draw our attention to that term. Okay. But what is this term? Well, this is just our two-level atom in an effective magnetic field, right? We have the detuning term and the Rabi frequency term. Our Rabi frequency is the two-photon Rabi frequency, omega 1, omega 2 over 2 delta. So this is my Raman Rabi frequency. And then I have a detuning. What is that detuning? Well, it depends on, this of course was equal to the difference between the laser 1 minus laser 2 minus omega 2-1, right? That's this detuning. This was what we call the 2-photon detuning. But there's this additional term. How do you interpret this term? And why does it affect the detuning seen in this 2-photon Raman transition? Yes?
Light shifted the 1 and 2.
That's right. So if level 1 and level 2 are light shifted, then even though the bare states might be in 2-photon resonance, the dress states aren't. So you will have to adjust your detuning to make it, to account for that intensity-driven detuning. That's actually a nightmare. It's a pain in the butt, and why often it's very hard to get this homogeneous and make this work well, because it depends on knowing what the intensity is, and if it's fluctuating or something, it's a problem. Okay? Yeah.
Do you want to, for the H-Raman equation, just
Yeah.
above the box equation?
Yes.
Do you want to add a delta term?
I do. I want to add a delta term. I left that out to
Between
this
what's
guy.
above and below?
Yeah, I do. So there is, thank you for reminding me. This has a minus H bar delta in it, for level 2. Thank you. So, but importantly, what this means is that I can, in principle, drive Rabi oscillations in the same way that we talked about them for an optically allowed transition. If I want to drive Rabi oscillations between two electronic ground states that are, say, separated by a microwave, I can do that through this 2-photon resonance. And I can do it with a much bigger effective Rabi frequency than I could with a honest-to-God microwave, because I can make the intensity of the laser beam much stronger. Otherwise, I'd need some big microwave cavity, and I'd fry everybody in the room, and that would be bad. So it's better often to not do that. This is done all the time, and that's how we control quantum coherence. It's what's, for example, done in an ion-trapped quantum computer. That's how the qubits are controlled, is through this kind of 2-photon resonance. All right. Very good. All right. Now, I want to return to this equation. And let's look at this in a slightly different way, in a different situation. Let's say that instead of going far off resonance, I'm going to go exactly on resonance. I'm going to make delta equal to 0. Okay? What happens in that circumstance in this lambda configuration? So I'm going to make lambda, I'm going to make delta equal to 0.
Then you can't do the stuff that you did
Exactly.
before
I
about
can't.
saying one has.
I can't do
small
adiabatic
parameter.
elimination. I can't do that.
Delta over gamma is no longer huge.
That's correct. So all of those assumptions are wrong now. But this is still right. This is the effective equation for what happens in the excited state. And there's no refeeding term there. But notice, so now let's just ask ourselves, what happens in steady state? In steady state, I just set that equal to 0, and I get right? But notice, there exists some choice of the Rabi frequencies, omega and 1 and omega 2, in which case, in steady state, this is 0.
Yeah.
So there exists choice of omega 1 and omega 2 such that that is 0. What is that choice? Well, that is a situation in which the ratio of omega 1 over omega 2 is equal to minus C2 over C1. Right? Under that circumstance, what we have is that there is no absorption. This is 0. This condition leads to what we call a dark state. What does that mean? What it means is that, let's take a look physically at what's going on. The dipole matrix element let's say I have some state which is in some superposition of the ground states. These are two sublevels, 1 and 2, which are both in the electronic ground state. Okay. And now I'm going to shine on this laser at my interaction Hamiltonian.
It's supposed to be C2 cut 2?
Yes. Thank you. So, if I look at this, my interaction Hamiltonian, there's only an allowed dipole matrix element that connects 1 to 3 and 2 to 3. So, let's say that, so let's look at the interaction Hamiltonian, the matrix element between that and that. That would drive me from the ground state superposition into the excited state. I'm going to get a minus so this is equal to omega 1, h bar omega 1 over 2, 1, 3 plus complex Hermitian conjugate, and then I have omega 2 connects 2 and 3 plus Hermitian conjugate. So this is going to be a C1 times h bar omega 1 over 2 times the dipole matrix element, if I care to include that. Let's see if I got this right. Hold on a second. good. Okay, yeah.
In that, in the second line of that H interaction equation, when you're leaving out some terms, is that, I believe you're leaving out terms, is that related to the RWA?
Yeah, we're always making the rotating wave approximation, indeed. So this is always we're always making the rotating wave approximation, and this is the effect of Hamiltonian, what we've always written down.
In other words, before you make that approximation, there'd be like an omega 2 times the 1,3 element, and omega 1 times the 2, 3 element.
No, that's not about the rotating wave approximation. There is something here that has to do with, so H bar, say omega 1 or omega 2, is the dipole matrix element between level 1 and the excited state and the electric field of 1 in units, right? So that is how we define the Rabi frequency, and similarly for 2. So this thing only involves this, and this involves this. There are terms, if we really want to do this out, of course, this laser is oscillating at frequency omega laser 1. This is oscillating at frequency omega laser 2. And there we go to the rotating frame and neglect the counter-rotating terms. So there are really terms here that look like e to the minus 2 omega laser. Those are the terms I'm neglecting. But there's no cross terms.
So,
It's in the rotating wave approximation.
but those D's are the same D's?
They are.
Upstairs?
They are. But these D's then become matrix elements. Okay, so now if we look at this, if I factor out the C1, then when that condition holds, this is 0. Right? If I plug in C2 over C1 is equal to minus omega 1 or omega 2. So, the important point here is that when I have this is equal to, so I have C1, right, so I'm going to make that condition omega 2, 1, minus omega 1, 2, and then I'll normalize it. So this is a normalized state which satisfies this condition, right? That the ratio of the amplitude of 2 to the amplitude of 1 is equal to that rate, right? This state is what we call a dark state. This state has no matrix element that connects it to the excited state. That matrix element is 0. Now, how can we understand that? Well, one way to understand that is that this is a quantum interference effect. Let's look at the specific case, just for simplicity. Let's say we tune the electric field amplitude or the intensity such that these guys are equal. So let's just assume we have chosen the laser intensities and the dipole for the given dipole matrix element such that that is true. Then what is the dark state? Well, in this particular case, this is a equal superposition of 1 and 2, but with a minus sign in between them, right? It's a 50-50 superposition of level 1 and level 2, but there is an important phase in the quantum superposition. And it's such that there are two paths of absorption. I have the situation where the atom is in a superposition state of being in level 1 and level 2. And there are two histories of absorption. There is one path of absorption in which it goes this way. There's another possible absorption in which it goes that way. But those two paths destructively interfere. And thus, I cannot get any absorption. If I was in the positive superposition, that is what we call the bright state. So I have a new basis of my system where I have an effective two-level system. The bright state, which is the equal superposition, the symmetric superposition, is coupled to the excited state, but the anti-symmetric superposition with the minus state is decoupled. And all I have is a coupling of the symmetric superposition, the excited state. Okay? That's an interesting phenomenon. You can also think about it in terms of the fact that there are two dipole moments, but they are, because of this minus sign, out of phase with one another, and they destructively interfere with one another. So there's one dipole that's going in one direction, the other dipole's going the other direction, the atom can't radiate. And since it can't radiate, it can't absorb. Okay. That's what this is talking about in this when one of these guys will give the minus sign. That's why this the effective dipole interaction is 0. Now, if we write down the equations of motion now that include the refeeding terms that I neglected, which you will do in your homework. You'll have lots of fun doing that. You have the following equations. So let's look at that. Right. And actually, when we talk, if I look at just what I want to look at on this situation, I'm going to look at the off-diagonal matrix element of the master equation, the coherence between level 1 and 2 that's driven on this system. So I'm putting on these two lasers. Each one of them is tuned exactly to resonance. And I want to ask, how does the coherence between these two states evolve in time? I'm not adiabatically eliminating anything. I'm writing down the exact equations. What I get is the following. So let's look at this. Actually, we were looking at the special case. These were equations in general. When delta equals 0, this is equal to 0. Remember, we had delta over delta squared. And when delta is 0, this is 0. Similarly, each of these light shifts is 0. Right on resonance. Yeah.
But we had, so for our Rabi rate Raman transition, that was in the approximation where delta was large.
Yeah, but I'm saying the more general formula was this one. So when delta is large, we had this over delta. When delta is 0, this is 0. And so I end up with the equation that looks like this. And I'm going to choose this again. Let's see. Right. So this then becomes equal to, and I'm going to also choose this to be exactly on 2 photon resonance. So I have this equation is this. And if I ask about the steady state, then what I find in steady state, this off-diagonal coherence is equal to this. Just setting that equal to 0, which is equal to this. But that's nothing other than the off-diagonal matrix element of the dark state. So the dark state is that, right? And so given that state, the density matrix for this pure state is that. And if I look at the off-diagonal matrix element between 1 and 2, I get that. So what does this tell us? This tells us that when I start the system in any state or other, it will ultimately absorb and emit photons. And in steady state, the atom is pumped, optically pumped into the dark state. That is what's known as coherent population trapping. Or CPT. That is to say, I can start the atom, say, in any state. It could be in a mixed state. It can come out of an oven. And now I'm just going to absorb and emit, absorb and emit, absorb and emit, and absorb and emit. And what this says is in that steady state, what I end up in is in a coherent superposition of these two levels with that phase. The atom is ultimately optically pumped into the dark state and will no longer absorb or emit because it is dark. Yeah.
I missed the last logic before the conclusion.
Yeah.
I see this row steady state, and then you said you can start in any state, even in a mixed state, and will end up in a dark state. How did you logically
Well,
get
what I'm
that?
saying is that this steady state here that I end up in, and if we all agree that this state is this state, that this steady state is in fact this state, then that steady state is independent of the initial condition. It's the steady state of a distributive differential equation. The initial condition is gone. If I have a differential equation which has damping in it, the steady state that I get Doesn't depend on the initial condition, those are transient effect, but just the drive. And that steady state is the dark state. Yeah,
How do you get it out of the dark state?
what's that?
How do you get it out of the dark state if you can't pump it out of the dark state because it doesn't absorb or emit
Yeah.
photons anymore?
Well, you're going to have to do something else to manipulate the coherence in that system in order to actually deduce properly. You're going to have to think about what measurement I'm going to do to know that it actually was in that state or get it out of that state. There is, of course, there are all kinds of other technical subtleties. For example, the fact that the atom is moving, and therefore that it has Doppler shifts. And those will typically cause the system to no longer be in the dark state. In fact, one of the ways you can try to cool atoms in a way that is different from friction is to make the dark state depend on the speed of the atoms. And that's known as velocity selective coherent population property, whereas the French like to call it VSCPT, because they invented it. And is one of the things that Hamiltonian won the Nobel Prize for, actually. This is a description of coherent population tracking. Now, we have a few minutes left. I just want to have a little food for thought. That's something we're going to pick up in a moment. Suppose I were to try, in contrast to what we did for the 2-level atom, for this 3-level atom, where I'm exactly on resonance, I want to look at what are the dress states. What are the dress states of this system? Well, as I was describing earlier, there are actually, this is a 3-level system, but one level is completely decoupled and doesn't interact with the light at all. So again, I'm going to put back in the omegas with some denominator. I don't really care about the normalization. So I have this state is decoupled. This state is going to be coupled to the excited state through some effective Rabi frequency. So now what I want to do is the following. What are the dressed energy levels here? Well, I'm going to have the dark state, and then I'm going to have a splitting. I'm going to have the state plus and the state minus. The state plus is going to be some coherent superposition of 3 and the bright state. The minus is going to be some combination of the bright state and 3. And this is the dark state. This splitting here, this guy is going to be independent of omega 1 and omega 2. No matter what omega 1 and omega 2 are, as long as there is some state, which is some superposition of 1 and 2, which is dark. Whereas this shift depends on what the Rabi frequency is. Okay. So now I want you to think about the following problem. Suppose, as a function of time, I do the following thing. Time. I'm going to turn on a pulse of light that is the amplitude of the electric field on laser 1. Okay? Yes, the other way around. Okay, so as a function of time, I'm going to turn on first this laser 2, and then I'm going to turn it off. And then intermediately, I'm going to turn this laser on and this laser off. Okay, so I have this pulse sequence. Initially, what is the dark state at when omega 1 is 0 and omega 2 is non-zero? When omega 1 is 0, the dark state is 1. Right? So out here, the dark state is 1. This is, say, as a function of time. Out here, when it's all laser 1 and no laser 2, what is the dark state? It's 2. And so I can, if this is done, so I turn on the laser slowly and turn it off slowly and turn this on slowly and that's off slowly. So let's say I start the atom here and I turn on this laser and then I slowly turn on that laser and turn this laser off. So I start by turning this laser on. What happens to the population? It goes from here to here. But that's backwards. If I want to transfer this to this, I do a Raman transition. We'll pick that up again next time. All right, we'll call it quits. I'll take your questions.
You were earlier